In the previous video, we followed the first chapter of Tony Hoare's book, Communicating Sequential Processes. We introduced the definition of a process as a coinductive record. We looked at a few simple examples. The stop process, which cannot perform any event. A clock process, which keeps ticking forever. And a couple of vending machines, each reacting to coins and chocolate in different ways. These examples showed how coinduction lets us describe systems that continue indefinitely, and how different processes respond to the same alphabet of events. We also introduced two basic operators on processes. The prefix operator, which forces a process to begin with a specific event, and the choice operator, which lets the environment decide between two possible events. Prefix gives us a process that performs one event and then behaves exactly as the given process. Choice gives us a branching point. If the incoming event matches the first option, we follow the first process. If it matches the second, we follow the second. If neither event matches, the process cannot proceed. These two operators already let us model a wide range of simple systems. We also looked at the trace of a process. A trace is just a finite sequence of events, recording the interactions a process has performed so far. Using this idea, we modeled the Diehard puzzle as a process. We solved the problem by following the state of the jugs through a sequence of actions. And we compared that solution with our earlier approach, using CTL. In this episode, we shift our attention from a single process to multiple processes. We will study relationships between processes, how they interact with their environment, and how systems can be built by combining simpler components. And to motivate these ideas, we will take yet another look at the Diehard problem. Before we start talking about processes interacting with their environment and with each other, let's do a quick warm-up. This example comes from Chapter 1, Example 8, on page 10. It is the run process. The idea is simple. At every moment, the process can perform any event from its alphabet. No restrictions, no branching, no stopping. Whatever event the environment offers, the process accepts it and continues as itself. This gives us the simplest form of an always ready, always responsive process. In section 2.8, Tony Hoare introduces an ordering relation on processes. Two processes are comparable only when they share the same alphabet. And we say that one process is less than or equal to another if it can do everything the other can do and possibly more. A quick note. In the broader CSP literature, the same symbol is often used for refinement, but with the direction reversed. Here we follow the definition exactly as it appears in Hoare's book. Formally, process P is below process Q. If every trace of P is also a trace of Q, mathematically, this relation is a partial order. It is reflexive, transitive, and antisymmetric. The first lemma shows reflexivity. Every process is less than or equal to itself, because every trace of P is obviously a trace of P. The second lemma establishes transitivity. If process P is below Q and Q is below R, then every trace of P is also a trace of R. So P is below R. Finally, if P is below Q and Q is below P, then the two processes have exactly the same traces. We call them trace equal. Let us establish a couple of basic theorems about this ordering. The first one is immediate. The stop process is below every other process. This is because stop has only one trace, the empty trace, and every process has the empty trace. Similarly, every process is below the run process. Run can perform any event at any time, so it contains every possible trace. If a trace belongs to P, it certainly belongs to run. These two results give us the smallest and largest elements of the ordering. Stop at the bottom and run at the top. Let us now take a brief detour into Bisimulation. This idea comes from concurrency theory, most famously from the work of Robin Milner. Bisimulation is used to relate two labeled transition systems. Two systems are bisimilar when each one can simulate the other step for step. Intuitively, two processes are bisimilar if you cannot tell them apart by interacting with them. Every move one process can make is matched by a corresponding move in the other. To formalize this, we start with a relation on maybe values. It says that either both results are nothing or both are just something, and those two values are related. Then we define bisimulation as a coinductive relation between two processes that share an alphabet. For every event, either both processes refuse to proceed, or both evolve to new processes that are again bisimilar. This captures the idea of matching behavior, step after step forever. Before we connect bisimilarity with the ordering relation, let us look at a few basic properties of bisimilarity itself. Just like the trace-based ordering, bisimilarity is a well-behaved mathematical relation. It is reflexive, symmetric, and transitive. The first lemma shows reflexivity. Every process is bisimilar to itself, because every step it can take is matched by the same step. The second lemma shows symmetry. If P can match every move of Q, then Q can match every move of P. And the third lemma shows transitivity. If P matches Q and Q matches R, then P matches R. Step for step, all the way down. These three properties tell us that bisimilarity is an equivalence relation on processes. Now let us connect bisimilarity with the trace-based ordering. The key result is simple. If two processes are bisimilar, then they have exactly the same traces. The proof is straightforward, though a little verbose. We pattern match on the possible responses of the two processes to an event. AGDA helps us by ruling out the impossible cases automatically. The first lemma shows that if P is bisimilar to Q, then P is below Q in the trace ordering. Every trace of P can be matched step by a corresponding trace of Q. The second lemma uses symmetry of bisimilarity. If P is bisimilar to Q, then Q is also below P. Together, these two facts give us trace equality. Bisimilar processes have exactly the same traces. Now let us look at how to represent a system built from two processes that interact with each other in lockstep synchronization. For now, we assume that the two processes share the same alphabet. When they run together, an event can occur only if both processes are willing to perform that event. In other words, every actual step of the combined system must also be a possible step of each component on its own. Here is the definition. For any event, X, we look at how each process responds. If either process refuses the event, the combined system cannot proceed. But if both processes accept the event, they evolve together, and the combined system continues as the parallel composition of their successors. This gives us a simple model of synchronous interaction. We can now look at one of the basic properties of this interaction operator. It is commutative. Whether process P interacts with Q or Q interacts with P, the combined behavior is the same. For any event, both processes must agree to take the step. So the order in which we write them does not matter. If both accept the event, they evolve to their successors, and we apply the same reasoning again. If either one refuses, the combined system refuses as well. This step-by-step symmetry gives us a bisimulation between the sides of interaction. We can also see that the interaction operator is associative. If we have three processes, The order in which we group them does not matter. Whether we first combine P with Q and then interact with R, or first combine Q with R and then interact with P, we get the same overall behavior. For any event, all three processes must be willing to take the step. If they all accept the event, the combined system evolves to the interaction of their successors. If any one of them refuses, the whole system refuses. This step-by-step matching gives us a bisimulation between the different compositions of the processes. We can now look at a couple of simple laws for the interaction operator. The first lemma shows that any process interacting with stop behaves exactly like stop. If stop cannot perform an event, then the combined system cannot perform it either. So P interacting with stop is bisimilar to stop. The second lemma shows that run acts as an identity element. Run is always willing to perform any event, so it never restricts the behavior of the other process. When we interact a process with run, we get back the original process. Together, these laws give us the familiar shape of a parallel operator with a bottom element, stop, and a neutral element, run. Let us now move to a more general form of interaction and talk about true concurrency. This time, our two processes do not share the same alphabet. When such processes run together, the rules change. Events that appear in both alphabets require the participation of both processes, just like before. But an event that belongs only to the alphabet of P is completely invisible to Q. Q cannot control it and cannot even notice it. So P may perform that event on its own. And symmetrically, Q may perform events that P does not understand. This means that the set of all events the combined system can perform is simply the union of the two alphabets. The code on screen captures exactly this behavior. We follow the same convention as in the book. We treat the alphabet as a single set A, and we carry Boolean functions that tell us whether each process can act on a given event. If an event is ignored by both processes, the combined system cannot move. If exactly one process accepts the event, that process evolves while the other stays where it is. And if both processes accept the event, they evolve together, just like in the synchronous interaction operator. This gives us a clean and flexible model of concurrent behavior. Let us understand this generalized interaction with a concrete example. And for that, we return to our familiar Diehard puzzle. We will solve the problem a third time, but now as a system composed of two concurrent processes. We treat Mclane, played by Bruce Willis, as one process. He controls the big jug. And we treat Zeus, played by Samuel L. Jackson, as a second process. He controls the small jug. Together, they form a system whose behavior is the combination of their individual actions. The alphabet for this combined system is simply the union of the events each of them can perform. Here's that alphabet. This function tells us exactly which events Mclane participates in. He is responsible for the big jug, so he performs the actions that fill or empty the big jug. He has no involvement in filling or emptying the small jug. Those are entirely Zeus's actions. But whenever water is poured from one jug to the other, Mclane must participate. A transfer affects both jugs, so both processes must take part in those events. This Boolean function captures that behavior. True for events Mclane can perform, and false for events he cannot. And this function tells us exactly which events Zeus participates in. He is responsible for the small jug, so he performs the actions that fill or empty the small jug. He has no involvement in filling or emptying the big jug. Those are entirely Mclane's actions. Just like before, whenever water is poured from one jug to the other, Zeus must participate. A transfer affects both jugs, so both processes must take part in those events. This Boolean function captures that behavior. True for events Zeus can perform, and false for events he cannot. For our current example, we can keep the process definitions extremely simple. Both Mclane and Zeus will accept any event from the combined alphabet. In other words, each of them behaves just like the run process. Both processes simply loop back to themselves after every event. Here is how we combine Mclane and Zeus to form a single Diehard process. The processes themselves are simple run processes. However, when we assemble them using the generalized concurrency operator, we obtain a system whose behavior reflects the independent actions of each jug, as well as the coordinated actions they must perform together. This keeps the focus entirely on the concurrency operator and the membership functions that determine which events each process participates in. Now we can check that the trace we already know is the solution is indeed a valid trace of our new concurrent Diehard process. Each step in the sequence corresponds to an event that Mclane and Zeus can perform, either independently or together, according to the membership functions we defined earlier. And because both underlying processes behave like simple run-style loops, the concurrency operator handles all the coordination for us. The lemma on screen shows that the entire sequence of actions is accepted by the combined system. So our third model of the Diehard puzzle behaves exactly as expected. This gives us a nice moment to recap the three different ways we have solved the Diehard puzzle so far. First, using computational tree logic, we modeled the puzzle as a labeled transition system and showed that there exists a path leading to the big jug containing 4 gallons of water. Second, we modeled the puzzle as a single process indexed by state, and we proved that when the process reaches the success state, the big jug indeed holds 4 gallons. And third, by treating Mclane and Zeus as separate concurrent processes, we showed that the familiar solution trace is also a valid trace of the combined system. One consistent solution across 3 different viewpoints and 3 different mathematical tools. So, we come to the end of this episode. Let's take a quick recap of what we explored today. We began with the ordering relation between processes, and we used it to define and reason about trace equality. Then we took a detour into Bisimulation, and we proved that bisimilarity implies trace equality as well, giving us a second coinductive way to compare processes. After that, we looked at interaction between processes. First, in the simple lockstep setting, where both processes share the same alphabet. And then in the fully generalized concurrency operator, where processes may act independently or together depending on which events they understand. All the code for today's episode is linked in the description. Feel free to explore it, experiment with it, and build your own process models.